Imagine I told you about objects that spit out entire galaxies, particles that travel backward through time, and stars so massive they could swallow our entire solar system like a grain of sand. You'd probably think I was describing the latest Marvel movie or a wild sci-fi novel. But here's the thing, I'm not. White holes, tachyons, quasi-stars. These aren't the products of Hollywood imagination or late-night creative writing sessions. They're real concepts, born from the deepest equations of physics, hiding in the mathematical shadows of our universe. Today, we're diving into 5 physics terms that sound so impossible, so utterly alien, that your brain might reject them as pure fiction. But as we'll discover, the line between science fiction and scientific reality is far thinner than you might think. Because sometimes the universe is stranger than anything we could ever imagine. Let's start with something that sounds completely absurd. White holes. Picture a black hole. You know the drill. Gravity so intense that nothing, not even light, can escape. Matter spirals inward, crosses the event horizon, and vanishes forever into the cosmic abyss. It's the universe's ultimate predator, devouring everything in its path. Now imagine the exact opposite. A white hole would be a cosmic fountain, a region of space-time that violently ejects matter and energy instead of consuming it. While black holes are cosmic vacuum cleaners, white holes would be cosmic fire hoses, blasting material outward with such ferocity that nothing could ever fall into them. Here's the mind-bending part. Einstein's equations don't just allow white holes to exist, they practically demand them. The same mathematical framework that predicted black holes decades before we actually found them also describes these theoretical cosmic geysers. But there's a catch. While the math says they're possible, physics makes them nearly impossible to observe. Any white hole would be incredibly unstable, likely lasting mere fractions of a second before collapsing or transforming into something else entirely. Yet some scientists wonder, could our entire universe have emerged from one massive white hole? Could the Big Bang itself have been the ultimate cosmic eruption, matter and energy exploding outward from some primordial white hole in a higher dimension? It's a tantalizing possibility. After all, if black holes are real, and we photographed them, why couldn't their opposites exist somewhere out there in the cosmic dark? Speaking of black holes, let me tell you about the day Stephen Hawking broke physics. It was the 1970s, and Hawking was wrestling with one of the universe's most fundamental puzzles. Black holes seemed to violate a basic law of thermodynamics. They had temperature, but they couldn't radiate heat. It was like having a campfire that never gave off warmth. Then Hawking had a revelation that would change everything. Near the edge of a black hole's event horizon, quantum mechanics goes absolutely wild. Virtual particle pairs, matter and antimatter twins, that normally pop into existence and immediately annihilate each other, sometimes get separated by the black hole's immense gravity. One particle falls in, while its partner escapes into space. The result? The black hole slowly, almost imperceptibly, begins to glow. This Hawking radiation is incredibly faint, colder than the cosmic microwave background radiation left over from the Big Bang. For a black hole with the mass of our sun, it would take longer than the age of the universe to evaporate completely. But here's the twist. Smaller black holes radiate faster, and in their final moments, they would explode with the energy of millions of hydrogen bombs. Hawking's discovery created a paradox that still haunts physics today. If black holes can evaporate, what happens to the information that fell into them? Does it vanish forever, or does it somehow escape in that radiation? The universe, it seems, is still keeping some secrets. Now let me take you back to the universe's violent infancy, to an era when the cosmos was still learning how to make stars. In those primordial times, roughly 13 billion years ago, something extraordinary may have existed. Objects so massive and so bizarre that they barely qualify as stars at all. We call them quasi-stars, and they were monsters. Imagine a star so colossal that it makes our sun look like a marble next to a basketball. These theoretical giants could have been thousands of times more massive than our sun, their surfaces extending far beyond the orbit of Earth. But here's the truly mind-bending part. At their core wasn't nuclear fusion, but something far more exotic. A black hole. An actual black hole sitting at the heart of the star like some cosmic parasite, feeding on the stellar materials around it and powering the entire object through pure gravitational energy. These quasi-stars wouldn't have lived long, perhaps only a few million years before collapsing entirely into supermassive black holes. But in their brief existence, they may have solved one of astronomy's greatest mysteries. How did supermassive black holes, billions of times more massive than our Sun, form so early in the universe's history? The answer might be quasi-stars, cosmic stepping stones that bridge the gap between the first generation of normal stars and the monster black holes we see lurking at the centers of galaxies today. We've never observed one directly, but somewhere in the deepest reaches of space, their fossil light might still be traveling toward us. Speaking of the universe's earliest stars, let's talk about the cosmic holy grail of astronomy. Population 3 stars. After the Big Bang, the universe was a dark, cold place. No stars, no galaxies, no light except the fading afterglow of creation itself. For nearly 400 million years, the cosmos existed in what astronomers call the Dark Ages, a vast, empty expanse filled only with hydrogen and helium gas. Then something magical happened. Gravity began to win. Slowly, inexorably, that primordial gas began to collapse and condense. Temperature and pressure climbed until somewhere in the cosmic darkness, nuclear fusion ignited. The universe's first star was born. These population 3 stars were unlike anything we see today. Forged from the pure, uncontaminated material of the Big Bang, they contained no heavy elements, no carbon, no oxygen, no iron. Just hydrogen and helium in their most pristine form. And they were giants. Without heavier elements to help them radiate heat efficiently, these first stars likely became massive behemoths, hundreds of times more massive than our Sun, and burning millions of times brighter. When they died, and they died quickly, in spectacular supernova explosions, they seeded the universe with the first heavy elements. Carbon for life, oxygen for water, iron for planets. They were cosmic alchemists, transforming the simple into the complex. Today, the James Webb Space Telescope is hunting for these ancient beacons, trying to capture their light from across 13 billion years of space and time. We're literally chasing the universe's first sunrise, searching for the moment when darkness finally gave way to light. Finally, let's venture into the realm of the truly impossible, tachyons. In the 1960s, physicist Gerald Feinberg asked a deceptively simple question. What if there were particles that always traveled faster than light? Not particles that could be accelerated to light speed, but particles that were born moving faster than light and could never slow down. He called them tachyons, from the Greek word tachys, meaning swift. And mathematically, they're perfectly consistent with Einstein's theory of relativity. Here's where things get weird. While normal particles gain mass as they approach light speed, tachyons would lose mass as they slow down. If a tachyon ever managed to slow down to light speed, it would require infinite energy, making light speed a barrier they can never cross, just like us. But the implications are staggering. If tachyons exist, they would experience time differently than we do. From their perspective, cause and effect could be reversed. They might arrive at their destination before they were even sent, creating paradoxes that would make time travel look simple. Imagine receiving a message before it was written, or observing an effect before its cause occurred. Tachyons would turn our understanding of causality inside out. Most physicists believe tachyons don't actually exist in nature. They're mathematical ghosts, useful for calculations, but not for reality. Yet they continue to appear in our equations, lurking in the mathematics like persistent mysteries. Because sometimes the universe speaks to us through impossible things. White holes erupting matter across cosmic voids. Black holes that slowly fade away. Quasi-stars powered by the very darkness at their hearts. Ancient stars that lit the cosmic dawn. And particles that dance backward through time itself. These aren't just abstract concepts buried in dusty physics journals. They're glimpses into the true nature of our universe. Windows into realities so strange that they challenge everything we think we know. Science begins with imagination, but it ends with discovery. And somewhere out there, in the vast cosmic laboratory that surrounds us, the impossible might just be waiting to become inevitable. After all, the universe doesn't care what sounds impossible, only what's true.
This is Beyond Revealed. Subscribe now, and join us as we explore the mysteries that lie within our world and far beyond.